Imagine a journey that not only traverses vast cosmic distances, but also cuts through the very fabric of existence. What if you could witness the birth of stars, or whisper with ancient civilizations? Today, we will immerse ourselves in the most mind-bending physics concept: travel through space and time. Is this merely science fiction, or a promising possibility awaiting humanity's exploration? Get ready for your perception of reality to be completely transformed. Welcome to SpaceTime's cosmic journey, where we explore the universe's deepest mysteries. In this video, we will delve into travel through space and time. Don't forget to subscribe to the channel so you don't miss other exciting cosmic exploration videos. If you find this video interesting and helpful, please like and share to support us.
Since ancient times, humanity has always been fascinated by questions about the nature of space and time. For Isaac Newton, space was a vast, fixed, and eternal stage where all events unfolded. Time was also an absolute, unchanging flow, passing independently of everything else. This worldview dominated science for centuries, shaping how we understood the universe and our place within it. However, everything changed radically at the beginning of the 20th century, when a brilliant mind emerged to challenge all our assumptions: Albert Einstein. His theory of relativity unveiled a completely new picture of the universe, where space and time were no longer two separate entities, but two sides of the same coin, intimately interwoven into a structure called SpaceTime. Einstein demonstrated that space and time are not fixed, but can actually bend, stretch, and warp under the influence of matter and energy. Imagine a stretched rubber sheet. When you place a heavy bowling ball on it, the sheet sags. Matter and energy in the universe do the same to space-time, creating these sags, which are the gravity we feel. This discovery opened the door to the boldest ideas, including the possibility of traveling through both space and time in ways that previously only existed in the imaginations of science fiction writers. The most fascinating aspect of Einstein's theory of special relativity is the concept of time dilation. It states that time does not pass at the same rate for everyone. If you move at very high speeds, close to the speed of light, time will pass more slowly for you compared to those who remain on Earth. This is not a far-fetched hypothesis, but has been experimentally proven numerous times. A classic example is the astronauts on the International Space Station, ISS. Although they only travel at speeds of about 28,000 kilometers per hour, after many months or years of working there, they actually age a tiny fraction of a second slower than their twin siblings back on Earth. The Global Positioning System, GPS, that we use daily also has to account for this time dilation. Otherwise, measurements would be significantly inaccurate.
This demonstrates that forward time travel is not only a possibility, but it is already happening. We are all traveling forward in time at a rate of 1 second per second, and for those who move faster or are in stronger gravitational fields, that rate will differ slightly. Time dilation is also a consequence of general relativity, where gravity plays a significant role. Near an object with immense mass, like a giant planet or a black hole, space-time is so severely warped that time passes significantly slower. A distant observer would see time crawling like a snail for someone near that object. This is an irreversible form of forward time travel, taking a person to the future without a way back to their own past. While forward time travel seems feasible and has even been observed, traveling back to the past is an entirely different story. This idea runs into a series of logical paradoxes, the most famous being the grandfather paradox. This paradox poses the question: If you were to go back in time and prevent your parents from meeting, would you ever be born to perform that action? If not, then who prevented your parents? Such perplexing questions have led many scientists, including Stephen Hawking, to ponder the feasibility of backward time travel. Hawking, in A Brief History of Time and The Universe in a Nutshell, proposed the chronology protection conjecture, suggesting that the laws of physics might conspire to prevent the emergence of time paradoxes. In other words, there might be a chronology protection agency in the universe ensuring that the timeline remains undisturbed. He once wittily hosted a party for time travelers, but no one showed up, further solidifying his skeptical view on the possibility of backward time travel.
However, skepticism does not equate to complete exclusion. Theoretical physics is always looking for loopholes or creative solutions to these paradoxes, such as the concept of the multiverse. If there are multiple parallel universes, changing the past in one universe might merely create a new branch universe, without affecting the traveler's original universe. This could resolve the grandfather paradox, but opens up more complex questions about the nature of reality and how these parallel universes might interact. One of the most intriguing concepts, which could open the door to both space and time travel, is the wormhole. Widely discussed in Stephen Hawking's works, wormholes are hypothetical tunnels through space-time, capable of connecting two very distant points in space or two different moments in time. Imagine the universe as a sheet of paper. You can go from point A to point B by traveling along its surface, or you can fold the paper and poke a hole, creating a shortcut. A wormhole is precisely that shortcut. Theoretically, a wormhole could allow you to reach a distant galaxy in the blink of an eye, or even a different point in the universe's history. However, for a wormhole to exist and be stable enough for travel, it would require a type of exotic matter with negative energy density, often referred to as exotic matter. This matter would act as a scaffolding to prevent the wormhole from collapsing. Unfortunately, exotic matter currently remains a theoretical concept, and we have no evidence of its existence or how to create it. If a wormhole could be created and maintained, traveling through it would not violate the local speed of light, but it would allow for traversing distances and time much more efficiently than conventional travel. This opens up a range of astonishing possibilities, from exploring hidden corners of the universe to reliving lost historical moments. However, whether we can create this exotic matter remains a major hurdle, making wormholes still a distant dream for physicists. Speaking of strange cosmic phenomena, one cannot fail to mention black holes, cosmic monsters with gravitational fields so strong that nothing, not even light, can escape them. With a singularity at their center and an encompassing event horizon, black holes have long been objects of both dread and scientific imagination. Carl Sagan, in Cosmos, captured their beauty and mystery, seeing them as symbols of the limits of human understanding. But could black holes be gateways to other universes or even time machines? According to the theory of relativity, time slows down significantly near a black hole's event horizon. A distant observer would see an astronaut falling into a black hole seemingly frozen forever at the event horizon, while for the astronaut, they would cross the event horizon quickly. This extreme time dilation has fueled the idea that black holes could be a means for future time travel. Another scenario, though highly speculative,
is the possibility that black holes could be entrances to wormholes or even white holes, a theoretical phenomenon opposite to black holes, where nothing can enter but everything can escape. White holes could represent the exit of a wormhole or another end of time. However, these ideas remain deep in the realm of theoretical physics and lack any observational evidence to support them. Furthermore, the immense tidal forces near a black hole would tear apart any object attempting to approach the event horizon, turning the dream of traveling through a black hole into a nightmare. Even if we could survive, information about our destination after entering a black hole remains a mystery, because inside the event horizon, all known laws of physics break down. At the smallest levels of reality, quantum physics offers an unusual perspective on space and time. The concept of quantum foam, proposed by John Wheeler and related to theories studied by Hawking, describes an incredibly chaotic space-time structure at the Planck scale, where tiny temporary wormholes constantly form and disappear. These quantum wormholes could connect different points in space and time at a microscopic level. However, they are too small and exist for too brief a duration to be used for any form of travel by macroscopic objects. We can think of them as tiny ripples on the surface of the cosmic ocean, insufficient to carry a large ship. Nevertheless, the theoretical existence of quantum foam still sparks curiosity about the fundamental nature of space-time and whether there might be ways to harness these phenomena on a larger scale in the future. However, currently, our technology and understanding of quantum physics are still too rudimentary to turn these ideas into reality, and harnessing the energy to manipulate space-time at that level seems like an impossible task, requiring a technological leap far beyond what we can imagine at this moment. So, what is preventing us from actually building a time machine or an instantaneous spacefaring vessel? The biggest obstacle is energy. To bend space-time sufficiently to create a stable wormhole or a significant time jump, we would need an enormous amount of energy, far exceeding the production capabilities of Earth's entire current civilization. This type of energy could be equivalent to that of millions of stars. Furthermore, maintaining an open wormhole requires exotic matter with negative energy density, something we don't know how to create or even if it truly exists beyond mathematical calculations. Scientists also face fundamental questions about the stability of space-time itself. Could tampering with its structure lead to undesirable consequences, such as the collapse of the universe or the emergence of unsolvable paradoxes? Even if all these technical and physical hurdles could be overcome, there remain deep philosophical questions. Time travel could alter our perceptions of free will, causality, and even the purpose of existence. It could create unimaginably complex ethical issues and might completely change the meaning of being human. Although theories like string theory and Hawking's M-theory in The Universe in a Nutshell have attempted to unify the fundamental forces of the universe and might offer new insights into space-time, they are still in their nascent theoretical stages and do not yet provide a clear roadmap for achieving time or space travel in the way we desire. Although the challenges are immense, the desire to travel through space and time continues to burn brightly in the hearts of humanity. Carl Sagan, in his work Cosmos, inspired millions with the wonders and limits of the universe. He showed us that exploring the cosmos is not just about searching for new stars or planets, but also a journey of self-discovery and the hidden potentials of human intellect. Even if we never build a time machine or a vessel that transcends the speed of light, studying space-time still helps us understand the fundamental laws of the universe more deeply. Every advancement in theoretical physics, every new discovery about the cosmos expands our vision and reminds us of the grandeur of science and the power of curiosity. Dreaming of going to the future or returning to the past or traversing distant galaxies is not just entertainment, but a powerful motivator for scientists to continue pushing the boundaries of knowledge. It shows that in this vast universe, humanity's capacity to ask questions and seek answers is infinite. And this relentless quest, whether or not the ultimate goal is achieved, is already humanity's greatest adventure. We continue to look up at the night sky, wondering about unsolved mysteries, and dreaming of a day when we can write new chapters of exploration ourselves, surpassing every limit we once thought impossible. Whether we can truly master the art of space and time travel remains a profound mystery. But our cosmic journey of understanding continues, leading us to new horizons. In the next video, we will journey beyond our cosmic neighborhood to explore exoplanets, a quest for a second Earth. Join us as we discover distant worlds and ponder the possibility of life beyond our solar system.